So my problem is it's just like it's the easiest part. I can figure out everything, but it's the easiest part. I know, I put it wrong too, obviously. Couldn't you be holy this nasty? I forgot to put this here to the 10%. Yes. Yeah.
If you're watching this video, I just realized I did not record the first half of class, so hopefully you can see everything on the board in terms of the steps that we did. We define our variables, we build the equations, and we plug it all into our calculator. So take a look at what's on the board. You can always email me and ask me questions.
Oh, no.
All right, let's continue. Now that was it for the word problems. That was it for using our system to using matrices to solve. Should we go back and use a matrix to solve a 2x2? Because all we did so far was use matrices to solve a 3x3. And maybe there would be some value in going back and looking at a normal system. Well, let's just take a look and see what we have left. Oh, in fact, yeah, we will be able to. We have one type of solution left, which is still technically a matrix method, but there are actually two different ways that you can use matrices to solve a system. And you say, what? 2 ways to use matrices to solve? That's so exciting. There we go. So method number 1 using a matrix. Method number 1 was called inverses, where you use a matrix inverse and you say the solution is A inverse times B. Method number 2 with matrices uses what is called a determinant. And you solve it that way. So you say, okay, well, that's exciting. I mean, we had graphing, systematic guessing, substitution, elimination. We can use matrix inverses to solve, but now you're saying there's a second way to use matrices? And yes, that's true. There's a second way to use matrices. Which begs the question, is there a third way to use matrices? Well, I don't know. The 2 ways typically taught are inverses and determinants. So let's take a look here. Determinants and Cramer's rule. We're on the last section, 8.5. It says the determinant of a square matrix can be calculated like so, at least for a 2x2. So let's do the 2x2 by hand, and then we'll see how to use our calculator to do it. So we have this matrix right here, okay? And let's just all assume that this came from somewhere meaningful. So let's say that we had a system of equations that look like this. 12x minus 7y equals 5, and negative 5x plus 3y equals 2. All right, I just made up the 5 and the 2 bit. My point is I want us all to see that if I did have a system of equations I wanted you to solve right here, well, you can immediately look at that and say, okay, well, what are all the different ways I could solve it? I could do substitution, elimination, graphing, or you can take the coefficients off of the variables x and y and turn it into a matrix. We've already seen that. We would take those coefficients, take the inverse, and then do x equals a inverse times b. But there's another way, and this other way is called the determinant. So you take your coefficients right off of your system of equations, and now you have this matrix here. And instead of calculating an inverse, you calculate a determinant. Like, I can already imagine in your head, you're like, oh, okay, so this way is called the inverse, and this way is the determinant. I mean, this way is the blubblebdibadop, and then this way is the fibonacci. Like, I mean, we use different words to represent different calculations. What are these calculations, and where do they come from? Who even invented, an inverse versus a determinant? Calling it by a name doesn't really explain it. Okay, so a determinant, in this case, actually does have a simple computation. The determinant of a matrix, A, B, C, D, is you multiply A times D, and then you subtract B times C. So that's how you calculate the determinant of a matrix. You multiply the diagonal to the right, and then multiply the diagonal to the left. So let's try that. Write it down in your own handwriting real quick. You've got this matrix, 12, -7, -5, and 3. And we're going to multiply downward sweeping to the right. So that gives us 12 times 3. I'm going to write it out. I know, we all know that's 36, but I'm going to write it out. And then you multiply the left diagonal, -7 times -5. What we're doing right now is calculating a determinant. Now, notice why I wrote it out so carefully with parentheses. There's a lot of negatives there. We have a negative times a negative, and then we're subtracting that. And if you're not super careful, you might end up adding that quantity instead of subtracting the quantity, or vice versa. So now, very carefully, I'm going to say, well, that's 36 minus -7 times -5 is positive 35. So 36 minus 35 is simply 1. And we say the determinant of that matrix is 1. Now again, you might say, well, so what does that determinant represent? That would take us far afield into a bigger discussion about what determinants represent. The key thing is that we can now use that determinant to find the solution to the system of equations that this matrix represents. The key thing is we want the determinant to equal a number, not 0. We need the determinant not equal to 0. Because if the determinant is equal to 0, then we can't use this method at all. It has to the determinant has to end up equaling a regular number. So now let's practice using our calculator. Let's use our calculator to calculate all of these determinants. You'll notice that the by hand method only works for a 2x2 matrix. We only know how to calculate the determinant of a 2x2 matrix by hand. We can do the 3x3 and the 4x4 by using our calculator. So let's go on in, edit our first matrix A to be a 2x2, and then type in the entries 12, -7, -5, and 3. Now we have this matrix, and if you're within the matrix screen and you go over to math, where we've never been before, you'll see that the very first option is determinant. So once you enter in this matrix, you'll go second matrix, and then from the next screen, you have the options of names, math, or edit. And you'll choose math. And the first option under math is determinant. So now you can go to your normal calculator screen and choose determinant, and then choose matrix A. And the calculation we're about to do is determinant of matrix A. And if you enter, what do you get? 1. So the calculator gave us the answer that we expected, which was the number 1. We can, if you're doing a 2x2 matrix, I think we might agree to just do it by hand, rather than taking the time to editing the matrix and then choosing the determinant option and then typing in A. I mean, it might actually take more time to use your calculator than just doing it by hand, considering the computation is so simple. You know, right diagonal minus left diagonal. The key is that you can see that both ways give you the same answer. Now, to do the 3x3 and the 4x4, definitely the calculator is the way to go. There is a technique for doing this by hand, and there is a technique for doing this by hand, but this would take half a page, and this would take a full page. And who wants to do that? Nobody. So let's try calculating the determinant of our 3x3 matrix. Again, everybody, just in case you missed it the first time around, the size of a matrix is always row by column. And so this is 3 rows by 3 columns, so this is a 3x3 matrix. So let's go ahead and edit a 3x3 matrix. And we're going to type in the numbers. All right. And I did the determinant of this matrix, and I got the answer -12. Did anyone else get the answer -12? So again, I'll just walk around the room and make sure everybody has found this option called determinant, and that you're getting the answer -12. If you have any questions at all, please let me know. You can go ahead and try the 4x4 matrix because it's the same operation. You just edit the 4x4 matrix, type it all in, and then choose the determinant option. Oh, great. Here we go, folks. Did it work, Annabelle?
I just want to make sure I was right.
Is it working? Oh,
Yeah, that's what I have.
That would work out? Okay. All right, so we can go ahead and do the last matrix. It's a 4x4. Now, folks, I sure hope you're using both hands. You know, sometimes I see people doing this all with one hand, and it seems very, very inefficient. Just pick that calculator up, hold it with your left hand. You can use your thumb to type the number and your right thumb to actually hit enter, and it makes the whole process go faster. So it's 1, 0, 3, 0, 2, 7, 1, 0, 0. Yeah. And so the determinant of this matrix, uh-oh, I don't think that's right. What did y'all get? Oh, -2? Oh, goody, I got -2. Walking around the room, I saw somebody had 0 and somebody had something else. So, folks, if you got something other than -2, go back into your matrix and look at the matrix by going to edit and find out where you made your typo. Because it's probably just a typo where you typed in a number incorrectly. So if you got 0 or something else, go back in and look at all of your numbers and just find your typo. Okay, so all 3 of these matrices then would be solvable using determinant methods, or what is known as Cramer's rule. Now, so here's a fella, Kramer, who came up with this method and now is forever famous because he came up with this method for solving a matrix. Essentially, the first method was inverses, and not every matrix was invertible. And the second method is called determinants, and you need the determinant to equal something other than 0, and then you can solve. So between one or the other, you hope that the system can be solved using your matrix, either using the inverse method or using the determinant method. Okay, well, that's just typing into your calculator and finding out what the determinant is. Now let's actually see the solution. Wait a minute, it didn't give us any systems to solve. Well, that's weird. There are no systems to solve. Did they give us any? It didn't. Okay, so we need to go back and just look at some 2x2 matrices. So everybody, let's go all the way back until we get to some systems. Ah, there we go. Yeah, let's do this. Go all the way back to the substitution method and the elimination method. Oh, better yet, let's go all the way back to the, boy, I wish I just had some equations that we could use. Didn't I give us equations in the original packet?
Did you have the substitution?
Yeah, here we go. Let's go all the way back to, oh, well, if you have this packet on you, it's the first packet that we did together. It just has a couple of problems that we can do. If you want, you can stay on the determinant page where you are and just write these down. You don't have to go back to the packet. We're just going to use these problems and solve them using our determinant method. And actually, not these. There we go. Yeah. I'm going to use these as an example. Okay, these are just examples. You don't have to flip back to the other packet. If what you'd like to do is just stay on this page where we just learned about the determinant and just go down to the bottom. We don't need a lot of space to solve these. Okay, so this is called Cramer's rule. And it gives a solution to a system using the determinant computation of a matrix. So first, let's go ahead and write down what this system looks like as a matrix. As a matrix, you actually write it down as one long matrix with all the numbers. So instead of a separate A matrix and a separate B matrix, we write down all the numbers. We write down 1, -6, -4, -5. You draw a little vertical line, and then you put in the answers, 17 and -10. We call this the augmented matrix or the full matrix. It just puts all the numbers into one matrix instead of two separate matrices. So here's what we're going to do. We're going to calculate 3 different determinants. The first determinant that we're going to compute is the normal 2x2 grid of numbers that we have right here. So we use straight lines now because we're computing a determinant. The first determinant we compute is the actual coefficients on x and y. So we're going to compute the coefficient, to compute the determinant of this. I want to show you all 3 at once. Let's not compute it just yet. And then we're going to compute a determinant called determinant sub x, where what we're going to do is replace the x coefficients with the answers. So for my first column here, which represents the x variable, let's all agree that represents the x variables, that represents the y variable, and that represents the numbers, right? 1x minus 6y equals 17, -4x minus 5y equals -10. We've got the x coefficients, we've got the y coefficients, and then the numbers that they're equal to. For determinant sub x, we're going to replace the x coefficients with the numerical solutions, keeping the y coefficients the same. That's going to be determinant sub x. You'll notice determinant sub x is when we replace the x coefficients with the answers. And then we will also compute d sub y, the determinant sub y, which is when we replace the y coefficients with the answers, keeping the x coefficients the same. So that right there, it's important to visually notice what we just did. The first determinant, just called d, is just the original coefficients from the variables x and y. So that's our normal coefficient determinant. To compute the determinant sub x, we're replacing the x coefficients with the answers. So you'll notice those are in blue because I replaced the x coefficients with the number 17 and -10, leaving the y coefficients the same. And then determinant sub y, I replaced the y coefficients with the answers, leaving the x coefficients the same. And that's the hardest part of this method right there, is just replacing the correct numbers with, that's the answers over there. Okay, so now let's compute those determinants. If you really want to compute those determinants using your calculator, you certainly can. You just have to edit 3 different matrices and then hit determinant of that matrix 3 different times. Or we can go ahead and compute these by hand, which I think is a little faster. So let's just recall. You do the right diagonal, 1 times -5, minus the left diagonal, -4 times -6. So again, that's the right diagonal minus the left diagonal. Right diagonal minus the left diagonal. Meaning, I'm drawing the diagonal to the right, I'm drawing the diagonal to the left. So I did my right diagonal minus my left diagonal, which is going to give me -5 minus 24, which is -29. It's probably helpful to draw that, use your pen or pencil and draw in your right diagonal, 1 times -5, minus the left diagonal, -6 times -4. Did I do that computation correctly? -5 minus 24 is -29. Okay, let's go again. Now for determinant x, we're going to do our right diagonal, which is 17 times -5, minus our left diagonal, which is -6 times -10. Again, that's right diagonal minus left diagonal. So what does that give us? 17 times 5, is that -85? Minus +60? So that's -145?
Yeah.
So,
yeah.
That is not really it. Oh, that is a negative, okay. Oh, good, okay. Moving along, now we compute determinant y. So again, I'm going to do it by hand. The right diagonal, that's 1 times -10, minus the left diagonal, which is 17 times -4. That gives us -10 plus 4 times 17 is 68. So that's 58. Now, right now I'm demonstrating to you how Cramer's rule works. Cramer's rule works like this. You take the system of equations you'd like to solve. Again, we're finding a point of intersection in space. We're finding a coordinate x, y such that I plug it in and makes both equations true. You take down all the coefficients from the 2 systems, or from the 2 equations. You first do the regular determinant, which is the coefficients on x and y. You compute determinant sub x, where you replace the x coefficients with the numerical answers. Determinant sub y, where you replace the y coefficients with the answers. You compute all 3 of those determinants, and you end up with these 3 different numbers, -29, -145, and 58. Now, what do you do with that? Well, here's Cramer's rule. The solution to our system of equations, the coordinate, the point in space where the 2 lines intersect, is given by the formula d sub x over d and d sub y over d. That's the actual formula. That's the formula you'd want to memorize. You take your x determinant divided by the regular determinant and your y determinant divided by the regular determinant. And if you take a look here, plugging in all of our numbers, d sub x is -145 over d, which is -29, and d sub y, which is 58, divided by regular d, which is -29. And you might look at that and say, ooh, that's some pretty terrible fractions. But in fact, 145 does divide by 29, it's 5. And 58 does divide by -29, it's 2. -2, that is. And that's Cramer's rule. Lickety split. It's just a process. It's a computational process. You'll notice it's not substitution or elimination or graphing. It's this seemingly incredibly arbitrary rule of computing the right diagonal minus the left diagonal, computing 3 different determinants, and then you get the answer. Now you might look at all that and say, that seems all rather magical. Is the answer correct? Let's find out. If we plug in 5 and -2, 5 and -2, that gives me 5 plus 12 is 17. That's correct. And then here that gives me -20 plus 10 is -10. That's correct. So this method of magic worked. I call it a method of magic because we have no understanding why this works, right? Like just at face value, looking at it, we're like, okay, great, Kramer, way to go. You did this totally arbitrary thing, and it works out. You know, at least with substitution and elimination, we can wrap our minds around why it works because it's algebra. We understand algebra, so substitution and elimination makes sense. Kramer's rule, just looking at it, doesn't make a lot of sense. And yet, it works. Provided what? What can't D equal? 0. That's why I said in the beginning that when you compute a determinant, the determinant has to be a number other than 0. And now you can see why. D can't be 0. Can D sub x be 0? Yeah, the numerator can be 0. That's fine. D sub x or D sub y can be 0, but D can't be 0. So our only stipulation in doing this rule is that D can't be 0, but D sub x and D sub y can be anything. Okay, so did you all put that down at the bottom of your page? And that used up the white space at the bottom? Should we do another one? Because, I mean, that's it. That's the process. That's how Kramer's rule works. Your only expectation using Kramer's rule is to do a 2x2 system. So we just did it. That was a 2x2 system. Now, just for fun, what if D is equal to 0? If D is equal to 0, can you compute the coordinate? You cannot. And so you'd have to go use some other method. If D is 0, you'd have to go back and do substitution or elimination or something like that. The good news is, if D equals 0, what does that tell you about the system? If D is 0, this method doesn't work, and therefore the system must be either parallel or overlapping. So Kramer's rule is going to work provided D isn't 0. It's going to give you the V point of intersection. And so that then implies that if D is 0, which means you can't compute a single coordinate in space. If you can't compute a single coordinate in space, that either means there is no single coordinate in space because they're parallel, or it's because there's not a single point in space, there's infinitely many points in space because they're overlapping. So Kramer's rule will work provided that you're looking at a system that either is oblique intersecting or perpendicular intersecting. That's the only way Kramer's rule will work. And you can check really quickly to see if a system is parallel or overlapping simply by computing the original determinant. This is really neat. If you just look at a system, like let's just look at this system right here. I'm gonna compute the determinant real quick of just the original one. So my determinant is -2, 3, 1, and 2. And so I'm going to compute that determinant. So right diagonal, that's -4, minus left diagonal, that's 3, that's -7. This automatically tells me that this solution, or this system has a solution. There is a point in space where it'll work. Whereas watch this. Let's say that my system was 2x minus 4, and then 1x, oops, y, it's 5. And then I'm going to do minus 2y. Then I want to make that one like that, and like that, equals 7. Okay, so take a look at that system. I just basically made this up. Do you know if this is parallel, overlapping, intersecting, oblique, or perpendicular? Of course not. Who could just look at that and know right off the bat? However, look at me. I'm going to compute the determinant real quick. 2, 4, 1, and 2. My determinant will be right diagonal, 2 times 2 is 4, minus left diagonal, 4 times 1 is 4. That equals 0. And since that determinant is 0, what does that tell me immediately about this system? It's either parallel or overlapping. Isn't that really powerful? This is really powerful. That just by computing a determinant of a 2x2 matrix, I can just immediately know, hey, this thing doesn't have a solution. It's either parallel or overlapping. And that's really neat. We call that an existence result. It tells me what the solution looks like without actually computing the solution. Okay. Part of me thinks we should do another one of these, but the other part of me thinks, oh yeah, you think we should do another one? Okay, let's do another one real quick. Everybody, you can set it up yourself. Let's do number 13. Number 13, you can just do this on a scratch sheet of paper. Begin by writing down the system. -2x plus 3y equals 16. and then 1x plus 2y equals 6. So there's our system that we're going to solve. Again, I'm just taking this from our previous packet. And recall, you're going to set up 3 determinants. Determinant d, determinant d sub x, and determinant d sub y. Where, remember, these are your answers. Those are the numbers that are going to be plugged in for the x coefficients or the y coefficients. So our original determinant is just the determinants of the variables x and y. So that's -2, 3, 1, and 2. Again, just setting this up is the hardest part. And I'll tell you, from all the times I've done this material, the biggest mistake is students swap these two. And then they end up with the wrong answer. So let's notice, what does d sub x tell you? What coefficients are you replacing? The x coefficients. I'm going to replace these coefficients with the answers. So the d sub x means replace the x coefficients. So I'm going to put 16 and 6 there. And I'm going to keep the y coefficients the way they are. So d sub x means replace the x coefficients. And then what does d sub y tell you to do? What are you going to replace? The y coefficients. So now I keep the x coefficients, and I replace the y coefficients with 16 and 6. You do have one of these on the test, by the way, Cramer's rule. It's going to look just like this. So now we compute our determinants. Again, you can do this on your calculator. I think typing it all into the calculator is more work than just doing it by hand. But it's up to you. You can do it both ways. You can do it by hand, and you can do it on your calculator and try it both ways. So right diagonal, that's -4, minus left diagonal, that's 3, and that's -7. Again, right diagonal, that's 32, minus left diagonal, that's 18, and 32 minus 18 is 14. And then right diagonal, that's -12, minus left diagonal, that's 16, and that's -28. So we just computed our 3 different determinants. Now we say that our solution, x comma y, I always write it down like this. I'm saying, okay, I want my solution, which is d sub x over d, which is dy over d, which means d sub x is 14 over -7, and d sub y is -28 over -7, which gives me -2 and 4. Isn't that such a nice, clean solution? Isn't that nice? There's not a ton going on. You write down your 3 determinants, and then you plug it into your formula, and that's Cramer's rule. Thanks, Kramer. It's just a nice, straightforward solution. So there we have it, folks. I think we're done. We've used so many different methods now. Graphing, guessing, substitution, elimination, matrix method number 1, which is inverses, and matrix method number 2, which is determinants. And now using all of these methods together, you essentially can solve any system. All we've looked at so far is solving linear systems. And a linear system means a system of 2 lines. So what does that leave us yet to solve? What do we have besides linear systems? Nonlinear systems. Nonlinear systems are systems where one of the curves, or both, or all, are not lines. So a nonlinear system could be a lot of things. A nonlinear system could be a parabola and a line. How many different ways can a parabola and a line intersect? You could have 2 intersections, or 1 intersection, or none. Can you have infinitely many solutions? This time, no. So a parabola and a line, 2, 1, or 0. What about a parabola and a circle? How many solutions can that nonlinear system have? A parabola and a circle could be once. A parabola and a circle could be twice. Really good question. Could a parabola and a circle ever be 4 times? Gosh, maybe. In fact, can anyone see how? Say my parabola looks like this. Can I have 4 intersection points? Sure. So this nonlinear system would actually have 4 solutions. Could you have a circle with a parabola with 3 points of intersection? Could it be 3 points of intersection? Yeah, you could even have a system with 3 points of intersection. So that right there is just the fun part, thinking about how many different ways can different shapes intersect each other. What about 2 circles? How many solutions could 2 circles have? None? Could you have a solution with 1 intersection point? Sure. Could you have a solution with 2 intersection points? Sure. Could you have a solution with 3 intersection points? I don't know how we get 3 out of that. I do not know. Could we have 4? No, I don't think so. I think at that point, that's just it. Okay, so those were some possibilities that we just brainstormed. Everybody, let's turn back to the last couple pages of our packet. All right, 8.7, systems of nonlinear. Okay, now you know how I always tell you that anytime you want to solve a problem in this class, you can just graph it? Well, that's true, except your TI calculators have a really hard time graphing these. It's tough to put these into your graphing calculator because you have to solve for y in order to plug it in. Because as you know, on your graphing calculator, it has to be y equals. So just look at, say, number 1. To solve x squared minus y equals 4 for y, that's not too bad. I'm going to move the y over here, and then move the 4 over there. So now I have y equals x squared minus 4. Okay, so I can graph that. But now look at the next one. X squared plus y squared equals 4. I'd have to solve for y, so I'd move the x squared over. So y squared equals negative x squared plus 4. And now I square root both sides, and I have y equals plus or minus the square root of negative x squared plus 4, which really means in my graphing calculator, I have to type in y equals the positive square root of 4 minus x squared, and y equals the negative square root of 4 minus x squared. So I've got that to graph for this equation, and I have this to graph for the first equation, and I'd have to graph all 3 of those simultaneously and see where they intersect. Okay, so is it possible to graph all these on your calculator? Yes, but you have to solve for y equals first on all of them. Desmos is a lot easier. Desmos, you can just type it in as it is. So notice, here's Desmos. There we go. With Desmos, you just get to type in an equation, just as you see it. So it's x squared minus y equals 4. There's our first one. And then the second equation is x squared plus y squared equals 4. There we go. It's a nice little picture, one that we just looked at. Oops. There we go. A circle intersecting a parabola. How many times does it intersect? You have to zoom in a little bit and really get close. There's 1, 2, 3, 4 intersection points. Okay? So let's think big picture now about what these problems are asking us. Section 8.7, systems of nonlinear equations and inequalities. It states, for number 1, solve that system. So everybody, let's write down on this very carefully together. Now, first of all, did we all see what that looked like? I'm going to draw a picture of it real quick. It was a parabola with a circle. I'm going to draw a good picture real quick. My parabola goes through the points -2, 2, and -4. Probably all of you want to draw this real quick. So there's a 2, a -2, and a -4. So that's my parabola. And then my circle is intersecting the y-axis at 2 and 2. Oh, in fact, it's intersecting the y-axis at 2, 2, and 2. So therefore, there's my circle. and it had points of intersection here and here and here and here. So 2 of the points of intersection were easy. It was 2, 0, and negative 2, 0. These extra points of intersection right below came out to be decimals, which was 1.732, 1.732, negative 1, and negative 1.732, negative 1. Okay, so conceptually, are we all together on what this problem is asking us? It says, hey, here's a parabola, here's a circle. How many times does it intersect, and where do they intersect? And using Desmos, I already just solved the whole problem. In fact, with a little bit of number familiarity, I recognize 1.732 as the square root of 3. So our solutions are actually root 3, negative 1, and negative root 3, negative 1. Okay, so those are all of our solutions. 2, 0, negative 2, 0, root 3, negative 1, and negative root 3, negative 1. Now you might say, great, Mr. G, on the test, can we just use our calculator? Again, the calculator is not a very good solution because you have to solve for y first, and you can't use Desmos during the test. But if you could use Desmos during the test, it would be just that easy. Now I just want you all to see the 2 equations that I just solved for y. Y equals x squared minus 4. There's that same parabola. Then I have y equals the positive square root of 4 minus x squared. That's the top half of the circle. And then y equals negative square root of 4 minus x squared. That's the bottom half of the circle. So do you all see that the 3 equations that I solved by hand produce the same picture? So could you do this on your TI?
Yeah.
Yeah. Your TI calculator could do this just the same as Desmos could do it. You're going to get the same picture. Regardless, how do you have to solve it on the test? By hand. By hand. Okay, so now that we've seen graphically what we're talking about, now let's go ahead and solve the problem by hand. Everybody ready for some excitement? Yes, yes, I'm ready for excitement. Good. It's really exciting. Now, I wish I had more space. Maybe I'll just go over here and solve it. Okay, folks, I'm going to solve some problems over here. So that was my solution up there. So now let's solve it. The problems were x squared minus y equals 4, and x squared plus y squared equals 4. Okay, thinking fresh. How can we solve this system? What are our options? Graphing. Will graphing work? Yes, we literally just did that. So graphing works. How about guessing? Does anyone want to try to guess the solutions? No, especially since the fact that we know that one of the solutions involves root 3. I mean, come on, who's going to guess root 3? So no, substitution. Can we do substitution? Yes, we can. We could do substitution right now. We could substitute one equation into the other. I just wanted to suggest it. Don't write it down yet. But substitution, remember, what do you need? A substitution sentence? So I'm going to make a substitution sentence. I could either solve for y. So I have x squared minus y equals 4. I'll move y to the other side. And then get y equals x squared minus 4. I now have a substitution sentence for y. And I can plug that in for that way or that y, and I can start solving. That's not incredibly exciting. I could also make a substitution sentence for x squared. X squared could be my substitution sentence. So now I take x squared minus y equals 4. I move the y over, and x squared equals y plus 4. That could be my substitution sentence, which is actually much easier. What if I make y plus 4 my substitution sentence for x squared? I now go into this equation, and I plug in y plus 4 in for x squared. And look what we now have. What do we now have? This is just a quadratic. We can solve this by factoring or the quadratic formula. Let's try it. I've got y squared plus 1y, and then that's plus 4, and another 4 on the other side. What happens to the 4s? They cancel out. I subtract 4 over to here, and we get y squared plus 1y equals 0. Now how do we finish solving? Here we just factor out the y, so now I have y outside of y plus 1 equals 0. This is the zero product rule, so something times something equals 0. That means either y equals 0 or y equals -1. Okay, I told you didn't have to write all that down, but this is a perfectly good example of substitution. So now what do? I have to go back and plug it into my other equation. So my first thought is that y equals 0. If I put y equals 0, I have x squared equals 0 plus 4, which is 4. And so if y equals 0, then x squared equals 4, which means x equals plus or minus 2. So that means that if y is 0, x can be plus 2, or if y is 0, x can be minus 2. Do you recognize those two solutions? Those are the two solutions, 2, 0, and -2, 0. So that worked. Now, that was if y equals 0. What if y equals -1? Now I say if y equals -1, then I have x squared equals -1 plus 4, which gives me x squared equals 3, which I square root both sides, and I get x equals plus or minus √3. Hey, that's where the √3 came from. And then I say, well, that's if y equals -1. So one possibility is that y is -1 with x being positive √3. And the other possibility is that y is -1 with a negative √3. And are those the other two solutions? They are. Okay, now I didn't have you write all that down. I just wanted to demonstrate for you real quick what these types of solutions will look like. So now let's do them together. Now, by the way, what we just did was substitution. Could we have done elimination? Could we have done elimination? Look at this again. We have x squared minus y equals 4, and x squared plus y squared equals 4. What variable could we eliminate? Now, only the x squared. Notice, can we eliminate y squared and y? Those are not the same variable. So even though that's one's minus and one's plus, you can't cancel a y squared with a y. But I can cancel an x squared with an x squared. So notice what I'm going to do is just change all the signs on this second equation, because this is a positive 1x squared. I want a negative 1x squared, so I make that negative, negative, and negative. I add these together. Those cancel out. And now I have negative y minus y squared equals 4 minus 4 is 0. This gives us back the same equation we just had. If I multiply those through by -1 again, I have y squared plus y equals 0. And again, you factor into y times y plus 1, and we get the same solution. Okay, that's enough just to demonstrate what we're talking about. Which solution should we do on this problem? Because now we're all about to write something down. Should we do substitution or elimination? Yeah, either one is going to be fine. And that's how we're going to solve all of these. Because I'll go ahead and tell you, you can't use matrix methods on these. If it's a nonlinear system, you cannot use matrix methods, not inverses, not determinants. Those are only for linear systems. So we're going to do substitution and elimination for nonlinear systems, and we're going to try both methods. So since it doesn't matter which method we're going to do first, let's go ahead and do substitution. So everybody ready? Let's do substitution. Just to make it more exciting, and because I want you all to see that you can do substitution sentence with an x squared, let's solve for x squared. So step 1, we need a substitution sentence. And that substitution sentence, we're going to solve for x squared. So x squared minus y equals 4. I solve for x squared. X squared is y plus 4. And that's what we're going to plug into the other equation. This is really neat that your substitution sentence does not have to be x equals or y equals. It can be x squared equals or y squared equals. It's up to you. All you need is an equation in which you can plug in something for a term that's in the other equation. So now, we take our other equation, which is x squared plus y squared equals 4, and I'm going to plug in, I'm going to write x squared empty. So I really have something plus y squared equals 4. And what are we plugging in there? Y plus 4. Now we write our terms in order. So we have y squared plus y plus 4 equals 4. And as always, you bring all of your terms to the left, which means the 4's cancel out. You subtract the 4, and you get y squared plus y equals 0. And then you always have two choices. You can factor or use the quadratic formula. This one's factorable by just factoring out a y. So you have y outside of y plus 1, which now we can use the zero product rule. We have something times something equals 0. And so either y equals 0 directly, or y equals -1. Now everything we did is just solving for y. Remember, we're solving for points of intersection. We're solving for coordinates in space, which means you need an x and a y. So far, all we know is the y values of the coordinates in space where this parabola intersects the circle. So now what do we do? What do we substitute our y values into? Back into our substitution sentence. Just like always. You start with a substitution sentence, plugging it into the other equation to solve your first variable. You take those two variables and plug it right back into your substitution sentence. So notice now we have to be a little more careful this time. Since we have two different values of y, we have to keep track of what we're doing. So I'm going to start with an English sentence. If y equals 0, then what? So if y equals 0, then we have x squared equals 0 plus 4, which means x squared equals 4. And if you square root both sides, that means x equals plus or minus 2. And that gives us two different solutions. So both solutions have y equal to 0. Right, so if y is 0, x is going to be plus or minus 2. So our two solutions both have y equal to 0. And now we just plug in either the positive 2 or the negative 2. And that's two of our points of intersection. Then we say our other scenario, if y equals -1. If y equals -1, then we plug it back in the substitution sentence. X squared equals -1 plus 4, which is x squared equaling 3, which you square root both sides and you get x equals plus or minus root 3. And now you set up your possible coordinates where y equals -1. And you plug in those two different possibilities that you have for x. Namely the plus root 3, the minus root 3. Now, how helpful was it that we knew ahead of time what the solutions were going to be? It's always helpful to know the solutions ahead of time, which is why I always encourage you to graph any problem that you ever do so that you know ahead of time what the solutions are. Because now we just did all the work to verify what we already knew. And so when they say solve, it means find the points of intersection, find the coordinates that you can plug in and make it true. So are our answers correct? Yes, we know they're correct because we graphed it. Well, let's say we didn't graph it. What would we have to do now? We'd have to plug up all 4 coordinates into both equations. Does that not sound like the worst thing ever? Plugging 4 different coordinates into 2 different equations? How many total substitutions is that? 8. You'd have to do 8 different substitutions to actually verify that your answer is correct. So when would you actually do all 8? If it mattered to you. Right? Do you want to get the problem right on the test? Well, then plug all 4 coordinates into both equations and check to make sure that they're both true. Do you have the time to do it? Of course you do. So that's how you'd finish the problem. Okay, so number 1 we solved with substitution. Right? So we're all done with number 1. We solved it with substitution. So how about for number 2, let's solve it with elimination. Everybody ready? Excited? All right. So elimination. This is actually going to be a really good solution. So we have x squared plus y squared equals 16. And we also have 16x squared plus 4y squared equals 64. Now, why do I say elimination is a good idea for this one? Yeah, because what do we need? We need one variable with the same coefficient but opposite signs. So this is already a positive 16x squared. It'd be very easy to make that a negative 16x squared. And then I can eliminate the x. Look at the y. This is already a positive 4y squared. It'd be very easy to make that a negative 4y squared by just multiplying through by negative 4. So let's eliminate the x variable first, shall we? What do we multiply through the top equation by so I can eliminate the x variable? Negative 16. So we have negative 16x squared minus 16y squared equals negative 256. That eliminates our x variable. And so now we have negative 12y squared equals whatever that is. Anyone know what that is? 64 minus 256 is negative 192. So we have negative 12y squared equals negative 192. What do we do next? Divide by negative 12. Y squared is equal to 16. Oh boy, that's convenient. Don't you just love it when you end up with something like y squared equals 16? Because 16 is square rootable, so you know you're getting a nice clean answer. So we square root both sides and we get y equals plus or minus 4. So keep in mind that's two different possibilities for y. So now what? We just did elimination. We have our y. What do we now have to solve for? X. So we're going to plug this in. Which equation should we plug it into? The original or the bottom one? I mean, which one looks better? The top one. The top one looks really convenient. It's just x squared plus y squared equals 16. So I would do the top one just out of sheer convenience. So now we're going to plug in first, set it up like this, folks. If y equals positive 4, right? Just really important that you set your work up carefully to say, okay, first, let's y equals positive 4. Let's explore that possibility. Let's explore the alternate reality in which y is positive 4. So I'm going to plug that into the equation x squared plus y squared equals 16. So if I plug in y is 4, 4 squared is 16, so that's x squared plus 16 equals 16. I subtract 16 from both sides. Oh goody, that means x squared equals 0, which means x equals 0. So what coordinate does that give us?
0, 0, 4.
Yeah, 0, 4, just that coordinate. Okay. So now we have to explore the other possibility that y is negative 4. So then we say, well, what if y is negative 4? Then we're still going to plug it into the original equation, x squared plus y squared equals 16. And so this time, what if I square negative 4? What's negative 4 times negative 4? Still 16. So x squared plus 16 equals 16. Subtract the 16s from both sides, x squared equals 0. Square root both sides, x equals 0. So now we have 0, negative 4. And apparently that's it. Apparently those are the only solutions. Just 2 points of intersection. What should we do? We should graph it and check to see if that's correct. So I'm going to come over here and graph x squared plus y squared equals 16, which is just a circle, and then 16x squared plus 4y squared equals 64, which is an ellipse. And there's our graph. And sure enough, we only have 2 points of intersection at 0, 4 and 0, negative 4. And were those our solutions? Yeah. Looks kind of like a weird cat eye, doesn't it? Okay. Now, I only have a couple minutes left, which means we didn't get to fully finish this. That's okay. We still have plenty of time. So now the real question is, what can I expect from you for homework? So these systems that you have here are going to work just like those 2 ways we just showed. You can either do substitution or you can do elimination. Since you're doing all these homework problems at home, I would have Desmos out and finding the actual graphical solutions first to help guide you to the correct solutions. Yep. Now, let's turn the page real quick and look at a graphical one. Folks, turn the page and look at a graphical solution. What do these problems even mean? What do these problems even mean? And we'll look at number 1. We'd like to know where x squared minus y squared is less than 1, and where x squared plus 4y squared is greater than or equal to 4. What do you suppose that graph looks like? Let's take a look. X squared minus y squared is less than or equal to 1. My graph I can only show equal to 1. So what would less than or equal to 1 look like? Wait a minute. Oh, remember our normal way is to put everything on the left and then say, where is it below the x-axis? So we're looking at all these points down here. Where is it below the x-axis? And then our second graph is x squared plus 4y squared minus 4. And when is that above the x-axis? No, no. This is going to take more time than I have right now. We obviously need to wait on this until next time. When is that greater than or equal to 4? Oh, look at shades. Oh my gosh, I didn't realize Desmos did this. Everyone look, this is so fun. There we go. So we were just able to graph both of those simultaneously. So we want to know, the first one is red, and so the shaded region represents the solution. And then the second one is green, and the green shaded region represents the solution. And we're saying, when are both true? When are both equations true? And you look at the graph and you say, where do you see both shaded? So can you all see where the graph is shaded by both of them? Hold on, where are they both shaded? Are they both shaded here? No, are they both shaded here? Are they both shaded here? Are they both shaded here? Yeah. So what we have here is a very interesting idea that this shaded region here, shaded by both, is the solution, and this region here is the solution. Okay, I'm probably not going to give any of these to you for homework or for the test, because this is just an abstract idea, and you need a graphing calculator to do this. The point is, when we say to graph both of those simultaneously and find the solution, you're looking for those coordinates in space that make both equations true. And so this region here is shaded for both of them, and this region here is shaded for both of them. So folks, let's just say I took this coordinate right there, that coordinate. What would happen if I plugged that coordinate into both equations? They would both be true. What happened if I took this coordinate and plugged it into both equations? One would be true and one would be false. What if I took this coordinate and plugged it into both equations? Both would be false, right? So I won't give any of this to you on homework or the test, but the idea is just the abstract notion of what solutions even mean. Okay, well, thanks, folks. I think a few of you, I still have to pass back your test. So if you're expecting a test, please wait a second. Jackie, Alexis, Jose, Jennifer, Perla, Melissa, Juan, Melissa, Juan, Jerry.
Right now.
Thank you, Kevin. Oh, I need my graphing calculators back, folks. If you have my graphing calculators, please bring them back. I still need 3 more. 3 more graphing calculators. Yeah. 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 Yes, sir, right here. Does anyone else have one of my graphing calculators? Please bring it back up.
Use late class. Why do I keep using late class?
Okay, so which one? Okay.
Here's your calculator.
Hey, thank you. Oh, good. Oh, good. Great. Okay, there they go. Okay, 8.1. And you said number 16? Okay. Oh, okay. Well, great. So you're just wondering how do you solve it? Do you have a piece of paper? Get out a sheet of paper so we can set it up. Okay, you're going to write it down. Okay, so remember, what's step one? Define our variables. How many children, students, and adults attend? So C is the number of children, S is the number of students, and A is the number of adults. Right, so each of those represents the number of people. Okay, so now we need 3 equations. One fact we know is that there are 241 seating capacity. Yeah. So that means that C plus S plus A must add up to 241. Is that fair? We're assuming that the theater is sold out.
Oh, yeah.
What's the next thing we
I've
know?
been here. Did you grab my phone?
The ticket sales were $17.36. So now that's total money. So that means that children is $5 per child, students is $7 per student, and adults are $12 per adult. And so now that gives us a total amount of money, which is $17.36. Okay, does that equation make sense? So $5 per child, 7 per student, 12 per adult, and we get $17.36. Okay, third equation says there are half as many adults as there are children. Half as many adults as there are children. So we have to think about this. If children is 10, then adults is 5. Or if children is 20, then adults is 10. Are we doing that right? There are half as many adults as there are children. Right. So adults is half the number of children. That's our equation. Now I don't like the fraction, so I'm going to say instead 2A equals C. So half as many children as adults, I just moved the 1/2 over the other side, so 2A equals C. I have to bring everything to the left, so that's really 2A minus C equals 0. And now in order of my coefficients, that would be -1C plus 0 students plus 2A equals 0. And that would be my third equation, which I got from there. Okay, Terry.
I just need to sign this.
Oh, okay. And then did you need a signature too, or are you just waiting
I'm
for Sarah?
freaking out.
Oh.
Yeah, I
Excuse me, Andrea.
Pardon me.